Okay, today we're going to look at some graphing skills. So by the end of this lesson, you should be able to understand the important graphing features we're going to look at today, and then also how to solve problems using your calculator. Okay, just some vocabulary. Axes, intercepts, those refer to x and y intercepts. Local maximum or local minimum. So those are local, referring to not necessarily the maximum point on the graph, but this is a local maximum, whereas the graph still continues forever towards infinity of y, but this is a local maximum and this is a local minimum, even though the graph continues towards negative infinity as x goes to negative infinity. So a local maximum or local minimum is a high point or low point on your graph. They're also called turning points. Domain and range, we've talked about that. Domain is all the x values. Range is all y values. Asymptotes, of course, we can have vertical asymptotes, which we write as x equals, and those are defined when we're dividing by 0. And horizontal asymptotes we write as y equals, and those are back to Bobo Button eats CC. And they're looking at the behavior as x goes to positive or negative infinity. Okay, so 2 examples we're going to look at. We're given this function, and we first want to graph that function on our calculator. So we'll graph so 2 to the x. Minus 2. Okay, so here's our function. We're going to find the axes intercepts. So we're going to find any x and any y intercepts. So we can look, we can analyze our graph. And the zeros will give us the x-intercepts. We can see the graph definitely does not touch the x-axis here. And we can analyze the graph here, and we can see our 0 is at 2, 0. So we know there's an x-intercept at 2, 0. As far as y-intercepts go, if you think about the function, the y-intercept happens when x equals 0. And likewise, the x-intercept occurs when y equals 0. And if you think about the function that we're looking at, when x equals 0, we have a problem. We're going to be, if we plug 0 in for x, we're going to be dividing by 0, and that's not possible. So when x equals 0, we actually have a vertical asymptote. So this function will never, ever equal 0 because of that. So there is no y-intercept. So there's no y-intercept because there's a vertical asymptote when x equals 0. Turning points of the function, so minimum or maximum points. So if we want to find our relative minimum, we can analyze the graph. We can find the minimum here. And we can see that it's at 1.44. Comma negative 0.116. So that's our only turning point of the function. If you look, you can see that this part of the graph is actually going towards a horizontal asymptote. And to find out what that horizontal asymptote is, you can use different tools. We could technically find the maximum here. We can see y equals negative 2 is our maximum, and we could continue to zoom out. As far as you want, and you can continue to analyze the graph. And again, find the maximum here and see if your function's increased at all, and you can still see it's y equals negative 2. So although it's not actually touching -2, our calculator just rounds to the closest value. So we do have a horizontal asymptote at y equals -2, so there's no maximum there. It's just going to continue as x goes to -infinity. So as it goes in the leftward direction, the function, y is going to continue to get closer and closer to -2, and it doesn't actually ever touch it, even though our calculator rounds to that value. So there's no maximum here, and likewise, because it's a vertical asymptote going towards y equals -infinity in this area, there's no relative minimum. Same with our vertical asymptote on the other side. So our only turning point happens to be at this relative minimum, and that's this point here. Okay, letter C, find any asymptotes of the function. So we've already talked about these. Our vertical asymptote is going to be any time that we're dividing by 0, so anytime the denominator is 0, and in this case, just x equals 0 is our vertical asymptote. And our horizontal one, we can't simply use boba but needs CC because we don't know, what that 2 to the x is going to look like. It's not just a simple power of x or x to a certain power. So we use the graph, and as we just noticed, we have a horizontal asymptote of y equals -2 as x is going to -infinity. And part D, state the domain and range of the function. So x can be anything except 0 because of our vertical asymptote. So for the domain, I'll just say x doesn't equal 0 for our domain, and our range, so we can see, if we zoom back in, remember y goes towards -2 here, okay, towards that horizontal asymptote. And then we found the minimum here, the relative minimum, and that's at y equals -0.116. So we know the function exists for every value of y except in between those two values. And we actually can't include -2, but we can include -0.116. Again, the function doesn't actually reach this value of -2. Our graph is just rounding to that on our calculator. So the range, we can say y is less than -2, so not including -2, or we can say y is greater than or equal to -0.116. We could also write that in interval notation, so we could say y goes between -infinity and -2, or including -0.116 to infinity. Okay, so that's our range. So y can be any value except in between -2 and this y value here, this -0.116. So we just want to make sure we're not including that in the range. And sketching the function, so showing its key features, you would just simply sketch this graph. We could do that quickly. So showing its key features, we'd show that we have a horizontal asymptote at y equals -2. We have a vertical asymptote at x equals 0. It's important to label those. We have a x-intercept at 2, 0. We have a relative minimum at 1.44, comma. So these are all important features that you would sketch on a graph. We would show our function getting really close to the horizontal and vertical asymptotes. Okay. So last example here, now we're going to sketch these two given functions. So we'll erase our first one. we'll sketch 1 over x, and our second one is 2 minus x, so we'll enter those as 2 separate functions. Okay, and we want our domain between -4 and 4, so we can x equals -4 and 4, so we can actually change our window settings. So we'll say between -5 and 5, just have a little extra space to view, and this can be like -4. Yeah, I just want to, yeah, okay. Okay, anyhow, you can play with the zoom, but so we've got our 2 functions. We want to find any solutions to this equation. So in other words, we want to try and figure out, is there anywhere where these 2 functions intersect? So we can go to Analyze Graph and Intersection, and it'll say lower bound, so we'll click below the intersection, upper bound, we'll click above, and we've got this intersection at the point 1, 1. So solutions to the equation, we're solving for x. So in this case, in our calculator, oh, that's nice. X equals 1. You can see that from the point. So the intersection is at the point 1, 1, and in that point, x equals 1. And when we're solving this equation, we're trying to find, okay, what is x? What is the solution to x? What does x equal? So the solution would be x equals 1. Okay. Okay, 1 solution, no solution, or 2 solutions. Okay, so notice first of all how this equation is related to this previous one. So let's put those in. Let's put that previous one, 2 minus x equals 1 over x. Let's put that in a similar form. If we add x to the other side, we get 2 equals 1 over x plus x. And when we solved this, we got 1 solution, right? So one of the ways that this equation, one of the values for k that's going to give us 1 solution, we know, is when k equals 2. Notice how this constant is equal to this constant because we've got x plus 1 over x, x plus 1 over x. We know when k equals 2 and the other side of the equation equals 2, we got just 1 solution. We had 1 intersection of those functions. And there also happens to be another one. If we make that -2 minus x instead of 2 minus x, we're also going to again get 1 solution. Oops. You can see again there's just 1 solution, there's just 1 intersection there. And that's when, and in that we get the solution -1. So that's when k equals -2. I use the equation -2 minus x and equaled that to 1 over x. So when we add x to the other side, we'll get -2 equals x plus 1 over x. So when k equals 2 or when k equals -2 is going to give us 1 solution. you can find that value -2 logically. You could also just play with different functions, experimenting with changing that line from 2 minus x to any constant minus x. So for example, we could try -3 minus x. And you can see, okay, now we've got 2 intersections with our function. And you can also see the same if we make that value +3. So again, we've got 2 intersections. So no solutions. Where are we going to have no solutions? Well, certainly if we just change it to -x, we're going to get no solutions. These functions are never going to intersect. So if you think about it, we get one solution when k equals 2, like we saw here, and we get one solution when k equals -2. So you can imagine if k is between those values, like in this example that I just graphed, k is 0, because we have y equals 0 minus x. That's the solution I graphed. Or that's the function I graphed. So if we want no solutions, it's going to be when k is between -2 and 2. So any value that we're adding to -x in between 2 and -2, we're going to have no solutions. So we could try, -1. And again, we get no solution. We could try +1, and again, we would get no solution. So the answer to number 2 here is k has to be between 2 and -2. I should have wrote that the other way around, -2 and 2. Okay, and then 2 solutions. Well, if we get one solution when k is equal to -2 or 2, we're going to get 2 solutions when k is less than -2. Anytime we move that line anywhere in this region, basically, it's going to cross the red function twice. So part 3, when k is less than -2, or when k is greater than +2, we're going to get 2 solutions. So for example, we already looked at this, but just to show you again, if we make it -4, it's a bit off the window, but you can see we'll have 2 intersections here. Okay, we can do the same with +4, which is greater than 2. So if we change our function to +4, you can see again we have 2 points of intersection. Okay, and that's it for today. Thank you.